I like the fact that I get to work a lot with the field people, not just sitting in the office.
Well, think about it. Everyone uses it every day. It's something that everyone knows, but it's still a mystery to everybody.
I like it because I don't do the same thing every day.
Everything is new. We're in a new market. We're expanding. We're inventing new things every day. You know, it doesn't get better than that as far as engineering.
So who are these people, and what is power engineering? Most of us know that power engineers deal with generating and moving the really big amounts of electrical energy. But what do power engineers really do? Actually, it varies a lot. Power engineers run major electrical transmission systems. They also build and design these systems. You might also find them in business sales or legal departments. And of course, there's inventing, but we'll get to that. When people think of power engineering, they usually think of something like the Bonneville Power Administration, located in the Pacific Northwest of the United States. Here, the BPA generates electricity and moves it throughout the West on major transmission lines. Toni Timberman is an engineer who works in systems operations at Bonneville. Her group keeps power flowing smoothly over BPA's 15,000 miles of power lines. She uses sophisticated computers to monitor the system and help plan for outages.
We simulate outages on the computer to see how the power system reacts. And then we watch the power system when we actually take that outage to make sure that what we predicted would happen actually is what happens, so that we can verify that our computer program is modeling correctly what actually happens in the real world. The most challenging thing is trying to predict what's going to happen in the future, whether we're going to meet the new loads that are coming up, whether we'll have a substation built in time to meet the new demand from next winter.
Other power engineers maintain systems. Rodney Dickens at New Jersey's Public Service Electric and Gas spends his days responding to all sorts of outages and line problems.
What I like to do first thing is get a handle on what operating conditions have taken place the night before. So I will look at our service dispatcher's log. They're the people that actually run the system, and see what equipments come in and out of service, where the service interruptions have occurred, and see if there's any specific action our department has to take to correct those situations.
Jim Farrell travels Michigan's Upper Peninsula, managing projects for MJ Electric, a construction firm that builds transmission lines for major utilities. Jim is young, likes the outdoors and the variety.
I spend most of my time estimating projects when they come into the office. And if we're successful with the bid, then I become the project coordinator and get the equipment and the material and the men out to the job site. Construction is a lot different than the design and engineering aspects of building a substation or a transmission line. There's a lot more to it than you realize before you start the job.
You know, when you think about it, we've become pretty blasé about our power. When we flip the switch, we expect the lights to come on and the music to play. And our standards have changed. Surges and fluctuations that were commonplace a few years ago now crash our computers and bring complex industrial processes to a halt. So utilities have put a lot of effort into issues like power quality and reliability, preventing problems before they occur. The alternatives, like outages and major blackouts, really aren't that attractive. At the BPA test labs in Vancouver, Washington, engineers go to great lengths to make components fail, then study the results. BPA test engineer Glenn Van Bergen even makes his own lightning in a special laboratory.
We can induce lightning through our impulse generator. We test different pieces of equipment, our switches, our ring-to-rod gaps, for withstanding impulse of lightning. Lightning impulse, switching surges, over voltages. Very important for safety.
And while Glenn is creating lightning in his lab, Jim Tillett tests relays, devices which sense trouble on a line and shut it down. Jim tests the relays with a computer system that simulates problems.
So this system basically plays waveforms or plays power line scenarios to relays to make them think that they're on a power line. The test setups are stored in the computer, and then the scenario is played out to the relays by a computer, and then the results from the relays are also recorded in the computer and stored in a database and the results can be viewed later.
To test substations, Bonneville sends this specially outfitted trailer into the field.
We're in Bonneville Power's shielded test trailer, and we take this out to do tests at substations. And part of that testing involves measuring quantities, voltage and current at remote locations, and in order to get those signals back to the test trailer, we use fiber optics.
Fiber optics, lightning generators, computer simulators. Bonneville's engineers use a variety of technologies to test components and a variety of engineering skills to solve problems.
Interact with people from all different backgrounds. Here at the laboratories we have people that have chemical, mechanical, civil, electronics and electrical degrees, and so there's just a lot of different mix of different work and different people.
Schweitzer Engineering Laboratories is a good place to see the impact of technical change. Consider relays. In the past, sensing a problem and shutting down a line was about all these devices could do. Today, Schweitzer designs relays that are smart. They use microprocessors to help reroute the electricity and locate the problem. Designing and building these relays requires new engineering skills, new knowledge, and creates new jobs.
I create algorithms that protect power system lines. The idea is just to create safe operation of electric power. So if there is a disturbance on any power line, we'll take care of it before anyone else finds out about it.
Right now I'm a hardware development engineer. What that entails is our research engineers and our application engineers and marketing and customer service will go out and find out what the customers want or need, and they'll draw up a specification and we'll come down here and design that for them.
Semiconductors are getting more and more robust in their strength and their utilization for larger voltages and larger current applications. And so the next level progression seems natural that maybe all of our power lines will be running solid state in the near future, and the only thing that will be mechanical will be the lines connecting them.
Well, I see power engineering becoming much more automated, so my job will become much more crucial to the operation of the power system, making sure that the power is protected correctly without having to have as many people involved.
So with all these changes in the ways we control and move electricity, what can we expect in the way electricity is created?
If you look at the cover of Popular Science magazine this month, there's a picture of a house which is shingled with solar cells. That's pretty neat. So photovoltaics isn't the thing normally that you would consider as an area of study or direct energy conversion at all for a power engineer in a traditional sense.
It's true. We don't usually think of solar cells when we think of generating large amounts of power. But the power industry has spent years developing alternatives to fossil fuel, and that research is beginning to pay off. The National Renewable Energy Laboratory in Colorado has refined power technology to the point where photovoltaics are now generating significant power.
This is where we test the photovoltaic modules for the U.S. manufacturers. The systems here are, several of them are tied to the grid. So right now, as we speak, we are generating electricity and pumping it back into public service power grid.
How do photovoltaics work? Dr. Larry Kazmersky explains.
If we look at this particular device, as I said, it's made out of silicon. It's a very, very simple device for electrical engineers. It's nothing but a diode. And when light comes onto the surface, the light is absorbed into this material. Its energy is transferred to the electrons, the negative carriers and positive carriers inside the semiconductor. The diode, the N side and the P side, give you a voltage, and so you have a voltage from the field that's put inside this device, and you have a current that's generated from the light, so you get power. If we look at our industry, of course, right now in the world, there are about 2 billion people who don't have electricity. And for power engineers, this has to be a rather large market you're looking forward to. If I go into Egypt, if I go into China, into India, where there are remote and rural applications for this technology, it might beat the extending the grid, the utility grid.
Besides photovoltaics, there are other promising technologies. One is Southern California Edison's Solar 2 project located in Barstow, California. No, it's not Stonehenge, but a field of mirrors or heliostats that focus sunlight onto a tower. The sunlight heats salt in the tower to over 1,000 degrees, making it a molten liquid. This superheated liquid can run through heat exchangers to drive turbines and make electricity. But the best part is, this solar energy can be stored.
What you are doing is you're taking sunshine and you're putting it in a bottle. And whenever you need to make electricity, you open up the bottle a little bit and you use the sunshine to make electricity. This solves a major problem with solar energy. Most people use electricity not when the sun is shining. You turn on your television at night, you turn on your lights at night, and there's no sunshine at night. And the big dilemma with use of solar energy, the most abundant, cleanest, most beautiful form of energy available, is it could not be stored.
The other big advantage of solar-powered systems is their impact on the environment. They reduce the amount of fossil fuels we consume and the emissions that go into our atmosphere.
Renewable energy is going to be the energy of the future. Whether it happens in the next decade or in the next 50 years is the only question. It is going to happen, and it is going to transform the way we live.
Remember wind farms? Well, the National Renewable Energy Lab has continued to work with the technology, and through the years, wind energy has become more and more productive. Engineers have faced challenges like smoothing out fluctuations caused by varying wind speeds and solving a number of mechanical problems.
The blades would break, the generators would break, it seems like everything would happen. So at the end of the first year, all the wind machines in California made enough energy for 2 houses. Now, I wouldn't tell that story if it weren't for the fact that year before last, all the wind machines in California made enough energy to supply the residential requirements of a city twice as big as the size of San Francisco. So that's getting to be real energy at that point.
What we have is a group of new technologies. They probably won't totally change the way we generate power, but they will change the mix.
All of them have benefits, and all of them have some limitations, and we have to balance these in our energy future. And I think it's very, very important for us as engineers is to use this balanced approach to understand. We have to make choices. Many of the choices we do as engineers are not only scientific, but they're also economic.
Power engineers will need new talents and skills, and their jobs will take them in some interesting directions.
For example, my organization right now is in the process of recruiting 2 international sales and application engineers that have the power engineering background, education, and experience. On top of that, have the sales experience.
But you can certainly get involved in legal and policy issues, the economics. Engineers have such a broad-based education that and their problem-solving skills have been so well-tuned that they can just have the flexibility to go anywhere with their career.
If you do get a BS in electrical engineering, you can go on and do other things. If you have a keen interest in generation or distribution or clients, services, you'll probably, and research of course, you'll find your niche.
The combination of an engineering degree along with a business administration degree kind of gives you the background that lets you understand the technical problems and maybe offer solutions, but also the ability to deal with the financial impacts of those problems and solutions.
There is a lot of opportunities there, tremendous opportunities for people with technical backgrounds, more specifically with electronics background or power engineering background.
So what is power engineering? It's a variety of technologies, some conventional, some new and exciting. Given our lifestyle, electricity isn't going to get any less important. Our need for power is growing, And so is our need for new ways of generating, managing, and marketing it. So power engineering is the challenge of satisfying this demand for power in creative ways. And power engineers are people who enjoy a challenge.
Power engineering is great. One day you could be working with 500,000 volts AC. Next day you could be working with lightning impulse generator, so you're inducing lightning. You may find yourself a week down the line that you're down on the DC intertie line, climbing a tower and taking a look at insulation on some of the problem spots that we have.
Couldn't think of a better place to be working in than in what I'm doing. I'm not only doing power electronics, but I do research, I write papers, I deliver reports, I come outside here where I actually get to install the designs that I come up with for these power systems.
I like computers primarily, and I get to work with probably the latest computer type software and hardware, and I get to do real interesting applications, and it's real mentally intensive.
Quite frankly, you never get bored. There's always something waiting to challenge you, to change your game plans, make decisions, set priorities, change those priorities, and then review the results.
If you like challenge, you like learn new things, you like making things, and you like see how things you make work, and you like the excitement of design something, you should go to power engineering.
So each day is a new adventure, and it changes. You can be outside. I'm kind of an outdoors person, so being able to go down the line and outside and working with some linemen, it's a great opportunity. You're not behind a computer the whole time.
I do love it. Yeah.
Well, there it is, a brief look at power engineering. If you'd like to learn more, check out our website at this address. Find out how your interest in science, math, and problem solving can lead to an exciting career with the next generation of power engineers.